So, Gabriel, are you running the poster session, or are you expecting that I was going to carry on to do that?
Yes, that's part of your session. So please, if you can share it, please go ahead. We have 3 posters there. The first one is near-term AI as an existential risk factor. I don't know if the presenter is there.
Yeah, I'm here. Shall I just please go right away?
Yeah.
Yes. So
cool.
The floor is yours, John, and also Benjamin.
Do you see that? Yeah.
Yes.
Yeah, we can.
Amazing. Cool. Sorry. So hi, yeah, I'm Ben, and together with Shiri, who we all heard from earlier in her great talk, together we've been looking at ways in which current and near-term AI could increase existential risk. So the main aim of our poster is essentially to explore how AI could potentially contribute to existential risk without the assumption of some currently hypothetical level of capability, such as artificial general intelligence or human level machine intelligence, or whatever you want to call it. And these sorts of assumptions have been fairly common in previous work on existential risk from AI, although this does seem to be shifting a little and assumptions are loosening. In particular, in this work, we focus on ways in which current AI systems could act as a risk factor, essentially how they could affect broader socio-political structures in a way that increases the likelihood of existential risk from other sources, such as biotechnology, or what's unfortunately in the spotlight at the moment, the use of nuclear weapons. And in doing this, we restrict attention further to 2 broad example categories of AI impacts, those of power relationships between nation states, corporations, and individuals, as well as how AI affects our access to information through, for example, its use in social media recommender systems that we've also heard about earlier today. So I don't know, that's all I had to say really. Thank you very much. And I look forward to seeing you in the session later.
Thanks.
Yes, that's it.
Okay. And next, is it Sheila presenting or Nikki? Are you there? Don't hear any response. So perhaps we should pass on to the 3rd poster, yeah? And then Gabriel, I'm afraid, as you know, I'm going to have to go shortly. But if are any of the speakers from the 3rd poster here?
Yes, don't worry. You can tell me when you are done and I'll take over.
Okay, thanks, Gabriel.
The presenters of the 2nd poster are there. Sheila Almani and Nikki Piscino.
Yeah, I couldn't see them. I didn't see them earlier, but maybe I missed them.
Well, let's call for the 3rd poster. I think that we can do that way, John, if you agree.
Yeah, certainly. So is John Mam or one of your colleagues here?
Yes, I'm on.
Okay, John, on to you then, sir.
Okay, is the screen being shared?
Yes, we can see that, thanks.
Great. So yeah, today I'll just present briefly some work toward interpretable local tree surrogate policies I performed in the Stanford Intelligent Systems Lab along with my co-authors. Okay, so basic idea behind this work is we want to be able to take highly parameterized, difficult to interpret models such as neural networks and represent them as more interpretable tree policies that are local surrogates to the original policy. So these are local policies in that they should maintain the behavior of the original policy with good fidelity in an area that is a subset of the full state space of the original policy. In this case, it's a forward reachable space rooted at some initial state. And they're represented as trees, which should provide more interpretability and predictability in the future behavior of the agent. So you can see here that if we look at each node of the tree, they represent an action taken along the trajectory of completing the task from the initial state. And each node also contains, compiles some statistical information about the probability of reaching that node along the trajectory and the expected value going forward. The algorithm can also be configured to compile problem-specific information. For example, in this case, leading to which states, giving information about which states will result in which action being taken along the search tree. The algorithm we presented to develop these trees are model agnostic, meaning they can be applied to any model type for the base policy. And we do so through a Monte Carlo clustering approach. In this approach, we generate a set of scenarios or determinized trajectories at the root node. And we roll these out using a simulator of the environment and the baseline policy layer by layer. At each layer, the scenarios are clustered in order to satisfy a distance criteria. In this case, we had a Q learning policy, so we used a distance criteria such that expected performance or Q value of each layer of the tree does not exceed a distance metric defined by delta shown here. That's pretty much the overview of the approach. I look forward to taking any questions at the poster.
Okay, thank you very much. I think that if the presenters of the poster are there, the dilemma between data transformations and adversarial robustness. Otherwise, I think that we can just wrap up the session today. Okay. José, are you there?
Yes.
Okay, I think that.
Yes.
What do you think?
Yes, I am.
Okay, I'm gonna stop the recording.